All right, today we're going to crack a kind of secret code that's hiding in plain sight on electrical equipment all over the world. It's called the Transformer Vector Group, and trust me, once you know how to read it, you'll see the world of power distribution in a completely new way. Let's jump right in.
So if you've ever looked at the nameplate on a big three-phase transformer, you've probably seen something just like this, DYN11. It looks pretty cryptic, right? Maybe a little intimidating, but I promise by the end of this, you'll be able to read it as easily as a street sign.
Okay, before we dive deep into the code, let's just do a super quick refresher on what we're even talking about. A transformer's main job is to take alternating current, AC voltage, and either boost it up to a higher level or step it down to a lower one. It's one of the most fundamental pieces of our entire electrical grid.
All right, let's start with the first part of our code, the letters. These letters tell us a story. They tell us exactly how the wires, or what we call windings, are physically connected inside that transformer box.
You know, for these big three-phase transformers, there are really two main ways to connect the internal wiring. The first one is called a delta connection, which looks just like a triangle, and it's represented by the letter D. The other one is a star connection, where all the windings meet up at a central point, and we use the letter Y for that. You might also hear it called a Y connection.
Now, here's a super simple but absolutely crucial rule. The case of the letter tells you everything. An uppercase D or Y always means you're looking at the primary or the high voltage side. And a lowercase d or y, that's always the secondary, the low voltage side. Simple as that.
And hey, sometimes you might spot a little N hanging out after the letters. This N is only for star connections, and all it means is that the central point where all those windings meet, the neutral point, is actually brought out as a terminal that you can physically connect a wire to.
So we've cracked the letters. Easy enough. Now let's move on to the numbers. And for this, we're going to use a really simple analogy that just makes it all click, a clock face.
Just think about it. A clock is a perfect circle, right? That's 360 degrees, and it's divided up into 12 hours. So if you take 360 degrees and divide it by 12, you get a nice round 30 degrees for every hour mark. This number, 30, that is our magic key to understanding the numbers in the code. So what are these degrees actually measuring? Well, they're measuring something called phase shift, or sometimes phase displacement. In the simplest terms, it's just the tiny timing difference between when the voltage wave peaks on the primary side versus when it peaks on the secondary side. The way the windings are connected inside actually creates this little shift in time. So here's the crucial part, how we read this clock. The number in the vector group tells you where the hour hand is. You just multiply that number by 30 degrees to get the phase shift. So, for example, the number 1 means a 30-degree shift, the number 5 means a 150-degree shift. And what about 11? Well, that's 330 degrees. We usually say the secondary voltage is lagging behind the primary, but what's really interesting is that a 330-degree lag is the exact same thing as a 30-degree lead. Think about two runners on a circular track. Being 330 meters behind is the same as being 30 meters ahead.
Okay, we've got all the individual pieces of the puzzle now. We have the letters for the connections, and we have the numbers for the phase shift. Let's put them all together and finally decode a real vector group.
Let's circle back to our original example, di11. Step 1. The capital D tells us the primary high voltage side is delta connected. Got it? Step 2. The lowercase y tells us the secondary low voltage side is star connected. Step 3. That little n tells us the neutral point on that star connection is brought out for us to use. And finally, step 4. The 11. We take 11, multiply it by 30 degrees, and we get 330 degrees lagging, which, like we just learned, is the same as a 30-degree lead. And there you have it. The secondary voltage leads the primary by 30 degrees. You just read the code.
Feeling pretty confident? Good. Let's put that new skill to the test with another really common one you might see out in the field, especially in industrial settings. D5.
Okay, let's break this one down real quick. D, primary, is delta. Lowercase y, secondary, is star. And the 5? We just multiply 5 by our magic number, 30, which gives us 150 degrees. So, in a dy5 transformer, the secondary voltage lags behind the primary voltage by 150 degrees. See? It's a totally consistent system. Once you get it, you get it.
So this is a neat party trick for engineers, but why does any of this actually matter in the real world? Why is this code so important that it's printed on every single three-phase transformer? Well, it turns out it's absolutely critical for safety and for the reliability of the whole system.
Understanding vector groups is absolutely essential for a few key reasons. First and foremost, it's for safely connecting two transformers in parallel to share a really heavy electrical load. It's also vital for making sure different parts of a power system can actually work together. And it even helps manage nasty electrical noise, which we call harmonic currents, that can mess with sensitive equipment.
And I really want to leave you with this one critical takeaway. This is the #1 most important reason this code exists. If you try to connect two transformers in parallel and their vector groups do not match, you are creating a massive phase difference between them. The result isn't just a little problem, it's a catastrophic short circuit. Getting this wrong can have truly severe consequences.
So, the next time you see a transformer, you won't just see a gray box. You'll see the story it's telling you about how it works inside. And it kind of makes you wonder, doesn't it? Now that you can read this language, what other technical codes are out there, just hiding in plain sight, waiting to be understood? Thanks for tuning in.